This is the second in a series of videos in which I'm attempting to develop a replacement ROM card for the HP9830 desktop calculator. If you're not familiar with the machine, then there are options that are supplied on cartridges like this, and these just contain a few ROMs and have software options in them, but these are becoming very hard to get hold of and hence very expensive. And what I want to do here is just make a simple PCB that can be used to use a more modern EEPROM, and the EEPROM can be programmed with the appropriate code and hopefully replace one or more of the modules, and then at least it makes the calculator more accessible, and people that own them can gain access to these additional software features. Now, I've done quite a lot of work with the 9830 previously in restoring one. I've been repairing a few more since then, and they're quite nice to work on. I quite enjoy working on them, but projects like this are particularly interesting, largely because of the way that the calculator works. It's a very discrete design. There is no actual processor as such. It is all discrete logic. And what we're trying to achieve with this card is to have the card send data into this bus. So this is actually a serial machine. It processes the data serially, but the memory is accessed in parallel onto a common bus, and then this register takes the data in, feeds the data out, but is also a serial register. But all the data from the various ROM cards, memory cards, etc. Come into this common bus, and as such it's important that all the data comes in the right way. It has to be inverted in some cases, not inverted in other cases, and of course it has to be put onto the bus in such a way that it's not going to conflict with the other cards. Now, most of the cards in the machine, such as the main ROM card, so this is the ROM card that I made a replacement for in an earlier video. These have got built-in open collector buffers on the outputs, the data output, and they also have level shifters on the address inputs. The ROM chips in these cards they're fairly easy to use, but they have some quirks. They run on 5 volts, but the control signals for selecting them, that's the select inputs, require 12 volt signals. They need a minus 12 volt rail as well, but the address inputs are TTL compatible, so it's kind of a mixture of technologies that you need to drive them. Also, the data comes out of them inverted, so that's again something that needs to be taken into account. The address lines may or may not be used in an inverted form. That's really system dependent. We'll come back to that in a few minutes. But the first thing I wanted to do, and this is a step that's not absolutely necessary for this project, but I find this quite a useful thing to do with this type of project, is I want to make a test jig so I can read an actual module. And the reason for doing this is when I put together my test module, my prototype modules, I want to be able to test them to make sure they're working properly before I plug them into the calculator. So the setup I've got here it's relatively straightforward. So looking back at the schematic for the cards, the module contains pretty much the same code as this, but does not have these buffers. The reason it doesn't have the buffers, if we go back and look at the schematic, then these are the slots that the modules are plugged into, and if we follow this back, you'll see that there is this arrangement here, and that's on a card in the 9830. It's not on the actual cartridges themselves, and this constitutes the same buffer arrangement that is normally within the actual memory cards themselves. So we don't need to duplicate that in our card. In fact, we don't want to duplicate it because we'd end up reinverting the data. Also, we have to bear in mind that the incoming control lines are 12 volts, so they're 12 volt signals, and we're going to be using them to control a TTL EEPROMs, so we need to be sure that we level shift those signals down. So there are 3 incoming signals that we'll need to do that for. The address lines are TTL compatible, so they'll be fine, and the outgoing data lines, 16-bit wide data bus on this, those lines, we can use the tri-state ability of the ROM. It is fed into a series of buffers, and if we look back at yet another schematic, we can see that the data bus from the ROM cartridges, unlike all the other cards, go through yet another series of buffers. So we're on the outside of these buffers, and so we are fairly safe to use the same mechanism that HP themselves did. The only difference is that the other modules will use Open Collector, whereas these modules use effectively a tri-state output on the ROMs themselves, and that's what we'll be doing. So once we've determined what we need in terms of driving this, then we look at this sheet. All this information is available online if you're interested in doing this, and it's this connector here we're interested in. This is the one that the cartridges plug into, and gives us the pinout for this, which is what I've duplicated here. And so what I've got set up is fairly simple. I'm using my programmer to essentially fool it into thinking that this module is one of these EEPROMs. It's very similar to what I did when I was repairing the machine I showed in a previous video series. This is just much simpler because it's a small card, much easier to drive. So I've got it all connected up the way it needs to be. I've got some level shifters to allow us to provide the required 12-volt signals for the 3 lines that need it. And then I've got a few inverters here to change the sense of the control lines so that the outcoming control lines from the programmer match what the actual card needs. And what I should be able to do now is use this to read this card. Now, because the data is coming out inverted, we'll end up with not only an inverted set of data, so the data will need to be negated before we can match it to what should be in the card, but also the address lines will be inverted as well. The address lines going into the card are inverse, so we're going to end up reading the data backwards. So we'll have to start at the end of the data will be the first byte, and we'll have to work back through the data in order to make sense of it. Okay, so I've printed off the first few bytes, or what should be the first few byte values from this particular module. This is in octal, and as I said, we will be reading the data backwards, but it doesn't matter as long as the replacement we make does exactly the same thing. So in other words, if it comes out of this backwards in this test jig, as long as it does the same thing when we make our replacement, then we'll know that it's going to work correctly in the target machine. I've got the laptop set up to read data from the programmer. I've got my O1 supply set up to provide the 3 rails. We've got plus 5 volts, minus 12 and plus 12. And those power supplies, by the way, for anyone that's interested, are still working fine. Haven't had a single problem with them. And we can now get this powered up, and we'll try and do a read of the actual data. So I'll bring up an overlay for the laptop screen so you can see it a bit more clearly, and we'll now try and do a read. So I'll power up the board or the test jig. So that looks fine. And what I'll do now is try and read the card. Okay, so that seemed to read fine. We'll now have a look at the data that we've captured. Now this is a 1K card, so we need to look at the, as I said, the top end of it for the first byte, because we are reading backwards because the address lines are inverted, but that will be at address 3FF, which is here, so it's this particular value. And if we get our calculator, set it to hex, and what I'll do now is convert that to the form that is in the printout. So that's 93F6. Okay, and we need to invert that, so we'll XOR it with FFFF and convert that to octal, and we've got a value of 66011. And if we look at the printout, we can see that the first value should indeed be 66011. We'll do it the next value as well, which should be 66036. So back to hex, and the value we've got that we read is 93E1, so we'll enter that, 93E1. We'll invert it, and then we'll convert that to octal, and we have indeed got 66036. I'll check a few more values, but it looks like we are correctly reading the ROM module board, so albeit in reverse. But as I say, that doesn't matter as long as it does the same thing when we make up our replacement board. The second reason I do this is to make sure that I've properly understood the interface, and I don't want to make a mistake on the actual calculator and make more work for myself having to repair it. So the fact that this is now working means that I've correctly understood the various control lines, the sense that they need to work in, and also if I want to, I can use this with a scope to do some detailed examination of the various signals and see what levels they are, what sense they are, whether they're active, low, active, high, that sort of thing. Okay, so that's it for this video. In the next video we'll start putting together and designing our replacement, but at least now we have a fairly firm understanding of what we need to be aiming for.